This video explains game theory and how you might be able to use it in an exam-style question. The most famous game in game theory is called the prisoner's dilemma, and it sets up a situation like the one here. So two suspects, Tim and Jenny, have been arrested and they're accused of a robbery. They're taken to separate police cells and the police give them these following circumstances. So if they both confess to their crime, each of them receive 5 years in prison. If neither of them confess, they both receive 2 years in prison. But if one of them confesses and the other one doesn't confess, then the person who confesses goes free, so no years in prison, while their accomplice goes to prison for 10 years. What you can see here is that the outcomes of each player depend upon the actions of the other player. That's a key feature of game theory, that what happens to one person depends upon the actions of the other person in the game. And we can represent this information in a payoff matrix, which is a visual and numerical way of showing this information. It looks like this. And from here we can see the outcomes, or the payoffs, to both players at each different position within the game. So for example, by looking at this cell here, if both Tim and Jenny confess, we can see that Jenny, who's represented by the bottom left-hand numbers in each cell, would receive 5 years in prison, and Tim, who's represented by the top right number in each cell, would also receive 5 years in prison. We analyse the game one player at a time, so we'll start with Tim, who will represent in blue, and we ask the question, what would Tim do if he knew that Jenny was going to confess? He has two options. He can confess as well, and he'd get 5 years in prison, or he could not confess, and he'd get 10 years in prison. The obvious choice is to confess, and so if Tim knows that Jenny is going to confess, he'll confess too, and take 5 years in prison because it's less than 10. If Tim, though, instead knows that Jenny is not going to confess, again he has two options. He can confess and get 0 years in prison, or he could also not confess and he'd get 2 years in prison. The best option for him is to confess, and that means that regardless of what Jenny does, whether she confesses or she doesn't confess, Tim's best option is to confess. We call that his dominant strategy, that regardless of Jenny's strategy, Tim's best strategy is always to confess. We then think about Jenny. We ask the same question, what would Jenny do if she knew that Tim was going to confess? Well, either she can confess as well and get 5 years, or she can not confess and get 10 years, and so Jenny, who we represent in red, if she knows Tim is going to confess, will also confess. What about if she knows that Tim is not going to confess? Well, either she can confess and get 0 years, or not confess and get 2 years. So if Jenny knows that Tim won't confess, she also won't confess and get 0 years. That means that Jenny's dominant strategy is also to confess. And that means the Nash Equilibrium of the game, named after the economist John Nash, is here, where both players confess, because confessing is both players' dominant strategy. That's interesting, because both players would be better off if they don't confess. They both receive 2 years in prison instead of 5 years in prison. However, if they can't communicate beforehand, their dominant strategy will leave them worse off, with both of them getting 5 years in prison. We can apply the same idea to businesses, primarily by thinking about the prices that two firms in the same industry might charge for a good. So both firms could charge a low price. If they both charge a low price, they'll both make £10 million in profit. They could both charge a high price, at which point they'd both make £20 million in profit. Or one could charge a low price and the other could charge a high price. If that happens, the firm that charges the low price will receive almost all of the customers, and therefore they'll make £25 million, while the firm that charges the high price will make just £5 million. Again, we go through firm by firm and think about each firm's dominant strategy. So starting with firm B, who again will represent in blue, if they know that firm A will charge a low price, if they charge a low price too, they'll receive £10 million of profit, and if they charge a high price, they'll receive £5 million. So if they know that firm A charges a low price, they'll charge a low price too. If they know that firm A is going to charge a high price, well, they can charge a low price and make £25 million, or a high price and make 20. So they're going to charge the low price. That means that firm B's dominant strategy is the low price. We do the same for firm A, who we represent in red. If firm B charge a low price, firm A will charge a low price too, because getting 10 million is better than 5 million. And if firm B charge a high price, firm A will charge a low price, because 25 million is more than 20 million. That means that both firms' dominant strategy is charging the low price. Therefore, the Nash equilibrium of the game is here, both firms charging a low price. We can analyse this as follows. So the Nash equilibrium is low price, low price. However, both firms will make a greater profit if they charge a high price. Both firms will make 20 million rather than 10 million. What that means, and this is the key takeaway from this game, is that there's an incentive for the two firms to collude or work together somehow to both charge the high price. That might include covert collusion, so secretly agreeing to both charge the higher price, because both firms will make a higher profit as a result, 20 million rather than 10 million. That's the way we use game theory in exams, to show that the Nash equilibrium is the low price, but that both firms will benefit from collusion. This game helps to explain why collusion might occur. We can advance the game and perhaps apply it to the firms. Two easy ways of applying game theory. Firstly, rather than saying low price and high price, you could use real prices if those prices are given to you in a case study. The other thing you can do is change the game so it's not symmetric. So now the payoffs are different for the two different firms if they charge the same price. What we see here is that if both firms price low, then firm A makes a higher profit, and if both firms charge high, firm A makes a higher profit. That means that firm A is the bigger company. The takeaway is still the same though. The Nash equilibrium is low price, but both firms are better off if they charge the higher price of £500. Therefore, again, there's an incentive for these two firms to collude so that they can make a higher profit